Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to arithmetic combinational logic circuits. Previously we discussed half adder and half subtractor. So in this video we are going to discuss about full adder. So before that, a quick review is that we implemented the digital logic circuits and we discussed some basic concepts related to 1s complement, 2s complement and the signed binary numbers, which are very useful in our understanding of arithmetic combinational circuits, which we'll see. So the digital logic circuits, which are divided into two parts. One part is combinational logic circuit, the second part is sequential logic circuits. In combinational logic circuits, there is no memory element present. It means the output at any time instant is dependent only on the present state of the input. Whereas in sequential logic circuit, output is dependent on both the present as well as the past state of inputs. So this is the basic block diagram of a combinational logic circuit block, where the internal circuitry consists of various combination of logic gates, basically AND, OR, NOT, or the universal gates NAND, NOR, or XOR, XNOR. It has certain number of inputs and certain number of outputs depending upon the requirement. These are the various types of combinational logic circuits. We were here. We discussed half adder and half subtractor. So now we'll discuss about full adder. Now if you remember, in half adder, the half adder, it was used to add only 2 bits, binary bits, in half adder. Like this. This. There was no provision to add the carry bits, whereas that is in half adder, these kind of operations it was not possible, which involved an extra carry bit. This is achieved it is not possible in half adder, but it is possible in full adder. So a full adder is a combinational logic circuit. It is an arithmetic circuit block which is used to add 3 bits. It has 3 input bits. The 2 normal bits as usual, which is present in the half adder, plus an extra carry bit, this one. This carry bit, the input carry, this is called as carry at the input side. So these 3 inputs are there on the full adder. On the input side, the 2 bits to be added plus the carry from the previous addition. And there are 2 outputs, sum and carry output. Let me give you an example which we discussed here. That is, let's say we perform the addition 0, 1, 0 and 0, 1, 1. So here there are 2 bits, so we can simply add 0 plus 1 is 1. Here there are also 2 bits, there is no carry, so 1 plus 1, the result is 0, this one. 1 plus 1, the result is 0 with a carry of 1. But here if you see, there are 3 bits in total, 2 0 bits and a carry bit. So it is 1 plus 0 plus 0. So 0 plus 0 is 0, 0 plus 1 is 1. These kind of operations are handled by the full adder circuitry, whereas these kind of operations can be handled with a half adder circuitry, combinational logic circuit. So this is what the full adder does. A, B, they are the 2 input bits, and this is the carry input bit. So here the result is the sum is 1 and there is no extra carry here, so carry output will be 0. So these are the 2 outputs of the full adder, the sum, the result, and carry generated on the output side. Here in this case there is no carry bit which is generated. For example, let us say we had an operation like this, where there is a carry of 1, we have the 2 input bits 0 and 1. So here 0 plus 1 is 1 and 1 plus 1 is 0 with a carry of 1. So here the result, the sum output will be equal to 0 and the carry at the output side, it will be 1. 3 bits. This is A, this is B, and this is the carry at the input side. The result is 0 plus 1, 1, 1 plus 1, 0 with a carry of 1. So here the output carry is 1 and sum is 0. Okay, like this. So this is what the respective input and output lines or bit lines they represent. A, B represent the 2 bits, normal bits to be added as usual, as was the case in half adder. Cin is the input carry, okay, the carry at the input side. S is the result of the addition operation, the 3-bit addition operation, and Cout is the carry which is generated at the output side. Okay, this. So from these operations you can be clear about what I am trying to say. So these two represent the 2 normal bits A, B. This is the carry input. Result is 0, the sum result it will be 0, and there is a carry generated, okay, from this operation. So this goes to carry output. Carry output bit goes high, the sum line or the sum output it goes low, depending upon the 0 which stands for low, 1 which stands for logic high, that convention. So sum will be 0, carry will be, output carry will be 1. Okay. Now how we can implement this full adder combinational circuit? So we have to look at the Boolean expressions of the sum and the carry output lines. So the sum output is given by this: A XOR B XOR Cin, the input carry, A XOR B XOR Cin, which can be written as A bar B bar Cin, or A bar B Cin bar, or A B bar Cin bar. So when I am saying A bar B bar Cin, it means A bar and B bar and Cin, because the product in Boolean algebra it stands for and the sum sign, the plus sign, it stands for or. Okay, so finally we have this output. Okay, A bar B bar Cin, or A bar B Cin bar, or A B bar Cin bar, or A B Cin. And the carry output is given by this: A B or A XOR B Cin. So this product again it stands for AND operation. So here it is, let me again clarify this is AND operation. So this is AND operation, okay, this, and these are OR, okay. This dot sign, the product sign, it is AND, and this is OR, and the bar, it represents NOT or inversion, bit inversion. The carry output is given by AB or A XOR B Cin, which is AB or BC or AC. Okay, actually the carry output is represented by this: A bar B Cin or AB bar Cin or AB Cin bar or AB Cin. The simplified form is this: AB or BC or CA or AC, Cin AC. Okay, so this representation of carry output, it will be helpful when we draw the logic diagram using basic logic gates, or especially when we use universal gates, NAND and NOR. At that time this representation will come in handy. So you can remember, I suggest you that you remember all these expressions. They are essentially the same thing. If you do this, you will get the same result. Okay, I will prove it in the upcoming videos. For now you just understand this. Okay, this is here. This is for carry output. Okay, this one, the C output, carry at the output side, and this is the sum, S, the result. So how we can implement it? So here, using these lines only, okay, these portions, sum is A XOR B XOR Cin, and carry output is AB or A XOR B Cin. Only by using these two expressions we can implement it using XOR gate, then this plus sign, so there will be a OR gate, and there will be AND gates required. So we will be using that, and we can form this logic circuit of full adder. So if you see, first we take the two input lines A, B, we give it to the XOR gate here, and we got A XOR B, okay, A XOR B here, and then we provided A and B to the AND gate, and we got AB. Okay, up to this it is clear. Then we gave this output A XOR B to one of the input lines of another XOR gate, and this carry at the input side we give it to the other input line. So we get here the output of this XOR gate A XOR B XOR Cin, okay, which is nothing but the final sum output. This line goes here, this is the final sum output. And we gave AB here to one OR gate at the output, and we gave C in here, so we used another AND gate and we provided A XOR B and C in. So we got here A XOR B and C in, and we provided these two to this OR gate, so we got finally AB or A XOR B into C, which is the carry output. This is the sum, which is A XOR B XOR C, and this is the carry out. So we used XOR gate, two XOR gates, two AND gates, and one OR gate to implement the logic circuit of full adder. Now there are other ways also. We can implement it using basic logic gates, not and or, only not and or. We can implement it using NAND universal gates, only NAND universal gates. We can implement it using NOR universal gates. So all those implementations we'll see in the upcoming videos. For now, you just remember this. Okay, understand this formation, logic implementation. And the most important thing is to remember these Boolean expressions, this and their variations also, because these variations will be used in implementing various the type of gate, logic gate you use, whether it is basic logic gates or universal gates, nor NAND, nor or not and or. Depending upon that, these Boolean expressions, the different variations of Boolean expressions will come in handy. Okay, next we have the truth table. So we have the three inputs here. From here to here, and these are the two outputs. So for the different input combinations, we have the following outputs. Okay, so this is the full adder truth table. You can test it. Okay, so this is the full adder truth table. So here we have discussed the basic concepts related to the basic logic implementation, Boolean algebra expressions, and the logical implementation using it. This is the basic implementation. Now there are other ways in which we can achieve the same result, which we'll discuss in the upcoming videos. So the most important thing here is to understand and remember the Boolean expressions of the two outputs, sum and carry output of full adder, which is this, and their variations. The sum, this is the carry output, this is one variation, this is one variation, and this is another. But they essentially represent the same thing, they mean the same thing. Okay, so this. So we have seen that the output carry, it comes in three forms. First one is A bar, B, C, or A, B bar, C, or A, B, C bar, or A, B, C. Okay, this is one form. Okay, then we have another form, which is C out equal to AB or BC or AC, and we have another form which is equal to AB or A XOR B, AB or A XOR B into C. These three forms of carry output for full adder is there. Now we will prove how this is equal to this using K-map implementation. Okay, we'll discuss that. Now our objective is to show how this is equal to this. Okay, so we'll take AB or A XOR B into C. So that is equal to AB or A bar B or A B bar into Cn, which is equal to A B or A bar B Cn or A B bar Cn. Now here we'll take B common in these two. So here we'll take B common, so we'll get A or A bar Cn or A B bar Cn. Okay, let us go to this side. Now if you remember the Boolean algebra law, something like x or x bar y is equal to x or y. So this is applicable here. So here it will be equal to B and A or C. A or A bar C, it becomes A or C, or A B bar C. So it is, so here it is equal to AB or BC or A B bar C in. So now here in these two terms we can take C in common. So AB or C in B or A B bar. Okay. Now here again we can apply this rule, x or x bar y. So here B or B bar A. So here it will become AB or C in into B or A. So here it becomes AB or BC in or C in A. So this becomes equal to this. We have proved it. AB or A XOR B into C in, this carry out expression is equal to this, AB or BC or C in A. So we have proved how AB or A XOR B into C in is equal to AB plus BC or AC. Okay, so this is it.